I'm Ramohan. I'm working as Head of Electronics and Communications Engineering Department at Government Polytechnic, Mahabubnagar. The topic of our discussion is inductors and transformers. The session will be confined for the discussion of the subtopic, that is specifications and the applications of the transformers. So the objectives will be as below. So on the completion of this session, you would be able to know the specifications of the transformers and also see the applications of the transformers. And before that, and we'll also see the losses in the transformers. So if we try to recap the topics we have actually discussed previously relevant to our present session. How many windings are present in a power transformer? Do you remember how many? So that will be having only two windings, that is the primary and the secondary winding. Then which term is used to measure the voltage and the current? You remember? So it's an instrument transformer that we use to measure the voltage or the current. Then which term is used to at audio frequency? Actually it has to be an AF transformer. Then further to recap, how many windings are present in a power transformer? This we have just now seen. Sorry, that's a repetition of the slide. So let us go for the specifications of the transformer. So let us see what this is. Do you have any idea about this? So this is the specifications plate of a transformer. So normally when you buy any device, there will be specifications chart mentioned on that. So this is the specification plate of a transformer. Here you can see transformer number or the model. Then you have some kVA rating, that is 100 kVA. Then you have high volts, no load voltage, low volts, then amperage 5.25, LV 139. So phases, how many? 3 phase. Some diagram is available or not, vector. So there are different symbols, and even on the right side there are more specification. The frequency 50 Hz, type of pulling, it is on. So likewise the weight, then liftable easy. So like that there are different specifications. So let us now actually try to understand what they mean to us and why they are all important for us. Now you can see this is also a transformer. You can see on that it is written as output transformer and 15,000 ohms single plate or PP plates to 600 to 150 ohms line. That means, so the output it is going to couple for 15,000 ohms, that means 15k, and that is going to couple on the other side with a 600 oblique 150 ohms line. That means there are two provisions provided on the other side. So this is like a impedance transformer. It's an impedance matching. So this is a normal transformer what we come across in power applications. So here you can see that the size is pretty big. It's about 20 centimeters. Larger one which is a center tap transformer. So as I told you, the first one is a impedance matching transformer. The next one on the right side you have many number of wires, that is a power transformer. So let us see its rating. So the input is 0 to 24 volts. There will be two wires on the primary side, and on the output there are actually how many? 5 wires, 3 yellow and 2 blue. So the middle yellow is the center tap, then you have blue and yellow on either side. So yellow on the extreme end is 40 volts, then blue is 24 0, then 24 40, and the current rating here is mentioned as 5 amperes. So these are few specifications of a power transformer. Hope you understood that. So let us further see into the specification of transformers. The signal transformers or the communication transformers are usually rated by their current rating, how much current it can handle. Then the other one is power rating. Then you have input and the output impedances for matching of the impedance matching. Then you have frequency range where it can work satisfactorily. So the frequency range is also important for the specifications of the transformer. Then some more transformers. The power transformers are rated by their primary and the secondary voltage normally, and then the power capacity, that is the voltage volt ampere capacity, like the power handling capacity of the transformer. So we are talking about the power transformers. So whether it is single phase or a three phase, so like that. Then let us see some more applications of the transformers as a list. So some of the applications of the transformers will be this: a step up transformer. So we are telling its uses. You also have step down. Step up is for transmission line purposes, where high voltage has to be transmitted put onto the cables for transmission, power transmission over long distances. Then step down for applications in our electron devices. Then a auto transformers, which gives a variable output. Normally it is from 230 to 230 will be input, so the output maximum will be 230 or less than that, up to 10 volts AC, and the current will be as good as that of the input. So you may have the capacity to draw 5 amperes of current. Then you have a current transformer, that is generally used for measurement purposes. Then you have a potential transformer. This is also meant for measuring applications in industry or labs. Then you have isolation transformer for the protection and the isolation of the primary circuit with that of a load circuit or vice versa. Then you have a protection transformer, so purely meant for protection of the load or the application device. Then you have power transformers, as it is meant for step down in radio or some other small voltage application, and also at power distribution. So they are all called as power transformers. Then you have a distribution transformer, so like at substations and at every corner of a lane, like you can see, there will be a distribution transformer. So the high voltage will be put on to the primary of the transformer, then the output will be down to 220 volts, that is required or supplied at household applications. So again you have a RF. So you have another RF transformer, so that is in radio communications, in a radio receiver or a TV receiver or some RF, that is communication equipment for wireless. Then you have high frequency transformers, similarly in communications again. Then you have a CVT transformer, which is called as a constant voltage transformer. So it has got some windings in wound in different directions to compensate for the changes at the input. And this transformer is designed to actually give a constant voltage at the output in spite of the variation at the input. So this is also used in laboratories while working or applying to the working tables of the laboratory, wherein we'll be working with all the experimental boards, so for the production and also constant response of that. So sometimes they are used in power transmission, the distribution system, and they are also used in stabilizers, once again for maintaining the output to be constant. Then they are also used for the electrical welding purposes, where you have high DC output, and likewise applications. Now let us see some more list of applications of the transformers. So the transformers are used in TV and photocopy machines, the transmission, the distribution of the AC power system we discussed. Again, they are also used in simple camera flash types uses. They are actually called as flyback transformers. So there actually for camera flash you'll be getting a high voltage, because of which it will be able to give a small high voltage for a small duration. Thereby the light coming out of flash will be very white and bright. Then you have signal and audio transformer. They are used for coupling in the amplifiers. So there's a highlighted message or the information which is telling that in today's transformer has become an essential part of electrical engineering, without which rather we don't exist, or the electronics does not exist. And also similarly electrical also cannot exist. Then you have the applications of transformers. Power transformers. So the power transformers are used in power supplies of the various electrical and electronic circuits such as radios, televisions, refrigerators, etc. On a radio circuit board, so we can see a radio circuit board, how it looks like. This is of course the basic radio which we have used at our childhood, though they are not available nowadays in the market, but it's a very good circuit. Here you can see on the right side there is a transformer, a filter, a capacitor, some diodes. Green one, if we can notice carefully, you can see there is green next to the capacitor. So that is actually a diode. So that is the power transformer in the radio receiver board. Here you have other types of transformers, different types you can see. So there are about 5-6 different types available on the board in our radio receiver. So this is another receiver, radio receiver. Actually here you have a transformer which is meant for radio impedance matching. So the circular one on the right side of your screen is actually a loudspeaker magnet part, and next to that is there are two transformers you can see. Somehow I missed that arrows to indicate them. Hope this is available in another side. Let us see. So that is actually, there are two transformers. They are meant for impedance matching purpose in radio receiver. Now let us see a TV receiver. So here it is a TV receiver, TV motherboard or the old model type with CRT type. So there are different types of transformers available. Then we have AF transformers that are used in audio stages of the radio receivers, amplifiers, and television receivers. So those transformers that are working at the audio frequencies, they are normally referred as the AF transformers. Why? Because they have to give a flat response for the whole audio frequency of the working range. So let us see AF transformers in a radio receiver. So this is another radio receiver circuit which you can see over here. Of course, and again a old model, which is an old model. So there are two transformers you can see, like enclosed in a circle with yellow line. What are they actually? They are actually the transformers working at AF frequency. They are also called as AF transformers slightly straight away, but they are also meant for audio impedance matching with that of the speaker actually. So one is connected at the input of a push-pull configuration of the final stage of the amplifier audio frequency range. So that will be used to apply input to the base of the transformer, of the transistors, both of the PNP and NPN for a push-pull configuration. And then the other transformer is to collect the output signal from the collector of the transformer, one for the PNP, the other for the NPN. And then the secondary of the output transformer will be actually used to couple that to the output from the amplifier to the impedance or the coil of the loudspeaker. So our load here is loudspeaker, so that is meant for impedance matching, as it is also mentioned on the highlighted red box. So actually audio transformers, they are most of the times meant for impedance matching also. So Z P is the primary winding impedance, then ZS is the secondary winding impedance of the transformer. Then you have the ratio, that is NP by NS as the transformer turns ratio. Then you have V1, that is VP by VS is the turns voltage ratio. Then from that, and from the older relations what we have, so we conclude it this way: the primary of the impedance ratio to that of secondary of the impedance will be equal to NP by NS whole square, that is primary turns ratio by secondary turns ratio square. That is also equal to voltage turns ratio of the primary square and voltage turns ratio of the secondary square. This means if the turns ratio or the voltage ratio is say 2 is to 1, then it will have an impedance turns ratio of 4 is to 1. So this is the meaning or understanding of the audio transformer that is used for impedance matching. So the impedance ratio will be related as shown here in the above equation, that is Zp by Zs equal to Np by Ns whole square or Vp by Vs whole square. Then let us see some more audio transformers for used for impedance matching. So here you have an example. Suppose you have an audio transformer with an impedance ratio of 15 to 1 that is used to be match the output of the power amplifier to a loudspeaker. If the output impedance of the amplifier is 120 ohms, then calculate the nominal impedance of the loudspeaker required for the maximum power transformer. Do you know what is the impedance of a loudspeaker normally? Yes, it is about 8 ohms. Let us see what happens here. Here you have the output impedance of the amplifier to be 120 ohms, and the impedance ratio is given as 15 is to 1. Now let us see how much it comes out to be. Let us calculate now from the equation what we have just derived previously in the previous slide. So it is Zp by Zs, that is equal to Np by Ns whole square, and that is given to as 15 is to 1. So if you equate that, so Zp is given as 120 ohms, Zs we have to find out, and Np by Ns whole square is given as 15 is to 1, that is 15 by 1. So if you take a root of that, it will become 3.873 divided by 1 whole square equal to 120 by S, from wherein you will be getting Zs equal to 120 ohms divided by 3.873 square, that comes out to be 8 ohms. So this is normally the standard impedance of a loudspeaker coil. So the impedance of the loudspeaker required will be 8 ohms for perfect maximum power transfer. So this is another impedance matching transformer. Here you can see, as on one side you have 4 watt, 8 watt, 16 watt and common. On the amplifier side of an amplifier, actually this is audio amplifier, a bigger one, and then the output secondary winding you have 4 ohms, 6 ohms, 16 ohms and 8 ohms tappings. That means the input also you can pick up. You have the choice to select what wattage you have to take into, depending on the output load, that is the loudspeaker you are going to connect. Again, you can also use different tappings of the secondary to match that of the speaker that is in your hand for the connection. And the right side one is the output transformer that is used for impedance matching again. Then you have at the bottom you have a circuit sort of a thing. So it is shown as an amplifier, then step up transformer 100 volts. So you give a audio input at the input side, then output you are getting 100 volts, so that will be connected to loudspeakers in parallel along the length of the wire. As see, this type of one is used in big halls and for stage performances where you will be connecting multiple loudspeakers for the horn type of loudspeakers, actually public speeches, that sort of application scenarios. Well, nice. So next comes the RF transformers. So RF transformers are used in tuning circuits of radio receiver, then in TV receivers. See, they are meant for basically tuning circuits. So tuning circuits are required as well as in radio receivers and also televisions, and also in transmitters and the receivers. So this is what the applications of the coils are. So in all the applications where actually the RF transformers are required mainly for the frequency selection and tuning applications. So let us see a radio receiver motherboard, an old model once again, the one we have seen if you remember previously. So here you can see there are RF transformers. They are connected to the RF amplifier for selecting the incoming frequency of the from the antenna. So for they are meant for tuning applications. So they form one pair. Actually, in a radio receiver, what happens? You will be having two coils which are interlocked rather. One is at the RF amplifier input side connected to the antenna, then a relevant or associated coil connected to the IF amplifier, sorry, not IF, that is at the mixer stage at the local oscillator. So these go two will be hand in hand, so they form one pair. So here we go, you have another pair which is being shown with a pink arrow. So they form once again one pair, one at RF, the other one at the mixer, that is at local oscillator. So these two actually pick up the required frequency of the input. They actually, we have two pairs, that means you have two band radio. This is a old model two band radio. You have a switch over there, band switch, so you can switch between medium wave, which is working at 700 or 650 kilohertz to 650 kilohertz, and the other one is short wave, so it goes in few kilohertz, megahertz, sorry. So they are, that is meant for that. Then here you can also see two more coils there. They are actually the IF transformers. So they are meant for input side as well as on the output side for frequency selective application, that is rather amplification. So the bandwidth of this frequency tune will be audio range, that is 20 kilohertz, and the normal IF frequency is 455 kilohertz, in which is the standard in the radio receivers. So you will be having these two IFTs, they are called, they are intermediate frequency transformers. They will be two, one at primary and the other at the secondary, sorry, at the input and output of the IF amplifier. So what we have understood is that the tuned circuits or the RF transformers are generally used in the radio receivers or communication equipment. So here we have just seen that this yellow arrow is indicating one set of transformers. They are for the RF amplifier, and these another pink arrows, they are showing another set of RF transformers. They are connected to the local oscillator and the RF amplifier of the input side of that. So they are actually switched between both pairs by using a band switch, as the radio receiver is meant for working in both the medium wave and the short wave frequencies. So they both meant for each band, one pair for another. So there are other sets, they are actually the IF transformers, as you have seen here. So they are IF, which is indicated by a blue arrow. Now let us see another application, that is IF transformers. So another application is IF transformers, which is actually used in radio receivers as well as the TV receivers, wherein it is meant for intermediate frequency. So in the radio receivers, the intermediate frequency used is 455 kilohertz, whereas in TV you have two independent IF frequencies, that is intermediate frequencies. One is 33.4 and 38.9. So these are IF transformers that are used in receivers. So there will be actually two or three stages of IF in a radio receiver normally. So they are of different sizes. Well, depending on the frequency and the current or the power where it is working with. Now the another application of these transformers is the pulse transformers. The pulse transformers are used to trigger the thyristors or the silicon resistors. Then they are also used for many other applications like change the amplitude of the pulse. So because pulse actually requires, it demands rather a very high bandwidth of the transformer to work with comfortably. So in some pulse transformer applications, it is also used to change the amplitude of the pulse. That is for different applications of triggering of different devices like ACRs or BJTs or sometimes MOSFET IGT FETs. So they need different amplitudes for triggering the gate of those devices. And for that reason, we also use this for changing the amplitude of the pulse. They are also used to invoke the polarity of the pulse. That is one application. And then further looking at the pulse transformers, we see practically in industry, this is actually a motherboard. I have actually picked it up from a UPS system wherein you can see three transformers. They are actually the pulse transformers. Actually they are used in the UPS for triggering the SCRs or IGBTs depending on the circuit whichever they might be using over there. So and here actually it is observed that each transformer is triggering 6 SCRs or IGBTs. Now the another application of this type of transformers is EHT transformers, and they are also called as actually flyback transformers. EHT stands for extra high tension transformers. These are actually used in television receivers and CROs mostly, where we require very high voltage for the plate of the CRT in both applications. So in televisions normally there is a requirement of about 24,000 volts to be applied to the plate of the CRT of the picture tube. So anode of the picture, and similarly for also in CROs also you need similar voltage. Then is it possible to have actually a transformer which steps up to that level? So normally we use step up transformers for stepping up for twice or thrice of the voltage. Like suppose you are having a line voltage of 230 volts, then you can get 460 volts, then again even adding to the double, probably you can get up to 1k. So here what happens, the relation to be maintained is the voltage for the, I mean the turns ratio for the voltage to be increased, doubled or tripled or whatever. So we have to maintain the turns ratio or increase the turns ratio at the secondary of the circuit of the transformer windings. So if you suppose you want to get 24,000 volts, then how many times the turns ratio should be? So it is, let us say 20 240 volts, you want 24,000 volts, so it is 100 times the turns ratio. So if you really do go for such an application of actually requirement designing, then the transformer will become very bulky, because the turns ratio has to be 100, 1 is to 100, which is practically impossible. So we use a different technique over here for generating this high voltage. We'll see what that is. And that is why it is called as EH2 transformer, or they are called as, principle is flyback. We'll see what that is. So this is how it is. So you can see that on the right side of the picture tube there is a rubber shield actually. So with that we use to connect the plate voltage to the picture tube. So the white one is the transformer, EST transformer, from where a red wire is used to connect it to the picture tube anode. So that is what it is. Then the transformer is called as the EST transformer or a flyback transformer. The principle is a different part beyond our scope of discussion at the moment. So extra high tension transformers, they are used in the TV resource for anode picture and also for CROs. And you also get them like this, a ready made high voltage DC generators, PCBs. So this includes EST voltage generation or rectification and filtering, and that's a module that is readily available for our applications. So you can see they are of different sizes depending on the size of the picture tube in both the picture tube in the TVs or a CRT, that is only the cathode ray tube. So basically we are talking about the CRTs. So based on the application it goes into a CRO or a television. Then we call in TV it as a, we refer it as a picture tube, which is a CRT rather. So you can see that they are of different ratings: 7 kilovolts, 15 kilovolts and 25 kilovolts. So, and they are also called as the flyback transformers. Well, for you to have a small understanding of the concept, in television receivers we use sweep generators for moving the raster in both CROs as well as the televisions. So in the raster you have trace and retrace. So trace is to write something information on the screen, and retrace is for the beam to come back to the initial position of the scanning. So while flyback it comes very fast. Normally in televisions 52 microseconds is the writing scan side and 12 microseconds is the flyback time. So during this flyback the actually beam is cut off to make it invisible on the screen or the raster. So and because here the flyback time is 12 microseconds and it is moving, the voltage is moving from plus V to 0. So this pulse is actually used to induce an voltage using an inductance, where the voltage in an inductor is equal to LdV by dt. L LdI by dt. So the faster the rate of change of current, the higher will be the voltage developed in the inductor. So we use this concept or the principle for generating high voltage in these type of applications, and that's the reason why actually they are called as flyback transformers. So these are used in televisions and servos as we have seen there. Now let us discuss about some of the losses that occur in the transformers. So as we know that the transformer does not have any rotating part, there is no friction and no binding losses. But then what are the losses? But transformer suffers from two types of different losses which are listed here. One is copper loss, the other one is the core losses, or they are also called as the iron losses or also called as insulation losses. So copper losses, they actually occur or they arise or they appear in the windings of the primary as well as the secondary, because we use copper wire, very fine drawn wire which is enameled or rather insulated. So though we try to see that the see that though we try to see that the resistance of the wire is minimum, still there is some finite resistance exhibited by the winding. So when the current is flowing through that, there will be also I square R losses. So these are called as copper losses, and it is reduced by selecting a thicker gauge wire for the winding. So the gauge means that diameter of the wire is selected to be high, so which actually reduces the resistance of the cable. Well, then let us see the other one, that is core losses. These are of three different types. One is flux loss, the other one is eddy current losses, then it is hysteresis losses. So flux losses. So this loss is caused when all the flux lines associated with the primary winding of the transformer does not pass through the secondary winding. This happens, and that is the reason why we say we use proper core, and that has to be taken care of. Depending on the distance or placement of the coils on the arms, all the magnetic lines of flux that is developed in the primary will not be actually passing through the secondary windings. So thereby we call it as flux losses. Some of the flux is lost in the free space. Similarly, eddy current losses. So this loss is caused by the flow of small local currents due to the induced EMF in the core. So when the magnetic lines of flux are passing through the core, it induces an EMF within the core, which is a metal conducting material of iron or ferrite, whatever. So that actually results in some current to flow through within the core. So they amount for the eddy current losses. This loss is reduced by using steel of high silicon content for the laminate fall. So we are trying to reduce it by increasing the quality of the steel that is used for laminations purpose. Then you have hysteresis loss. So a small amount of the energy is lost each time the AC primary current is reversed. So this is called as hysteresis loss. So when positive half cycle is flowing, what happens? So the flux will be developed in one direction. But when the direction during the second half cycle, it just gets reversed. So the flux that is flowing in the core is in one direction. So immediately it is changing. The moment it is crossing zero, it is getting reversed. So in this process, there will be some hysteresis loss because that is resulting in some magnetism. So they are in the opposite direction. So some energy will go waste in that purpose for that purpose. So this we can minimize. So this is reduced by using a suitable core material like soft iron and silicon steel. So this actually reduces that problem of hysteresis loss. Now let us conclude this session by looking at the summary and see where we are or what the things we have covered so far. So we have discussed about the specifications of the transformers. Then we have seen different applications of the transformers where they are used for and the purposes for which they are included in any application. Then we have also actually seen some of the losses in the transformers. Now let us actually try to recap or check our memory by answering few quiz questions. Dash transformers are used in power supplies of various electrical and electronic circuits. What do we call them? Power transformers, current transformers, or voltage, or any of the above. So they have to be called as a power transformer. So they are called as power transformers. That is choice A. Now, eddy current can be minimized by dash in the core. Do you remember? By laminating the core. If you remember well, we are not using a solid material for the core. We are using laminate sheet and using these laminations to achieve the required cross section area of the core. Then mention the factors on which the hysteresis loss depends. One is the quality and amount of the iron in the core, then flux density, frequency, and all of the above. Choice is all of the above. So they actually depend on all the quality of the material, amount of iron in the core, flux density, and also the frequency. So these are the factors they will decide on the hysteresis loss. Then one more. How does change in the frequency affect the operation of a given transformer? Does it have any relation? So iron loss increases with a decrease in the frequency. The higher the frequency, lesser the iron losses or core losses. Copper loss in the distribution transformer is independent of the frequency, because copper loss is I square R, so it has got nothing to do with factor F. So this is what we have to remember. Then normally, what can be asked, frequently asked questions from the discussions of the topics we have covered. So list the specifications and the applications of the transformers. Then list the applications of the power transformers. Another question that is possible is list the applications of the transformer in real life. Okay. Then what are the different losses occurring in the transformers? Then mention the losses in the transformer and explain them briefly. So these are the probable questions that can be asked in the session we have discussed, that is that in the topics that we have discussed from the exam point of view. So thank you very much for being with me for all the time during this session. Thank you very much. Hope it is useful for all of you. Thanks a lot. Thank you.